If you find some aspects of this talk interesting or otherwise controversial, you can download it from here and write me about the things that you don't like or that you prefer that I change or whatever you feel like. 100 years of cosmology from spiral nebula to the CMB. So why do I say 100 years of cosmology? Well, really, the whole idea of understanding the universe as we know it today really started about 100 years ago, literally, from 1912. But that's not to say that people didn't have theories about it. Many of us know stories from the Greeks and their hypotheses about the universe. They weren't based on much in the realm of reality. But many people have been thinking about it. Many people are looking at things in the night sky, trying to figure out what they were, of course, from the very beginning. I think Al-Sufi is probably the first person that's recognized to actually have identified the Andromeda Nebula and written it down on paper. Of course, the Aboriginals in Australia certainly knew about the large and small Magellanic Clouds. Al-Sufi has also claimed to know about the Magellanic Clouds. I'm wondering about these Dunhuang maps from about 670, whether or not they also have mentioned, because Andromeda Nebula is not that faint. You can see it with the naked eye. Probably other people have put it in maps, we just have lost those. But just to talk about a few other people who have tried to see, galaxies, but they didn't know they were galaxies. They were called spiral nebula as opposed to normal nebula, nebulous cloud-like things. People like Simon Marius von Utzenhausen, I love that name. He observed Andromeda back in 1612 using a telescope. John Hevelius, Maupertuis, his nebular stars, as he calls them, dense crowds of stars, that's what he thought they looked like. Thomas Wright in 1750, probably the first person to realize that the Milky Way is not just a universal sphere, because in 1750 the universe was the Milky Way. He realized our universe looks kind of flat, and it looks kind of disc-like. Probably Thomas Wright was the first person to realize that back in 1750. Immanuel Kant's famous island universes, again, that's based on these elliptical stars that Maupertuis had found back in 1745. He had the idea, well, maybe these elliptical stars are not just elliptical stars, maybe they are galaxies kind of like our own. So he came up with this idea, this island universe idea. Laplace also picked up on that. But it really isn't until 1868 that the first stellar Doppler shift is measured for a star. So a lot of speculation, but not a lot of data until about that time. So this is kind of the beginnings of cosmology, thinking about our universe. I mean, in a quick summary here. This, of course, is about 10 talks in itself. But one thing you're going to see in this talk, by the end, is that science is not a linear process. Probably many of you already know that, except for those students that haven't actually started doing a lot of science. But another thing is this belief by Planck, and it's been picked up by other philosophers, which I think you'll see is true here as well, that new scientific truth doesn't triumph by actually convincing its opponents. Those opponents, they pass on, and the next generation picks up those ideas and runs away with them. And we'll see that happens to all kinds of great minds, including Albert Einstein. So let's first talk about the size and nature of our universe. So I said that modern cosmology started about 100 years ago, and that started with Vesco Melvin Slipher. You will see he's probably the best dressed astronomer you'll see. Edwin Hubble comes close, but he always has a pipe in his mouth, and this guy goes into the pipes. You can see he has a beautiful cravat here. He observed at Lowell Observatory's 24-inch telescope. He was looking at these spiral nebulae, in particular Andromeda. He made a 6-hour and 50-minute exposure. So the next time students complain about observing runs, ask them, can you sit in front of a telescope for 6 hours and 15 minutes and track it? I wonder. September 17th, 1912, he found that this object, the Andromeda Nebula, was traveling at an amazing minus 300 kilometers per second. You say, so what, 300 kilometers per second? Nobody had seen a Doppler shift from an object in the night sky more than maybe 10, 20, 100 max. So this was a real shocker. Like, what is this strange thing? They had some ideas. You can see this picture from Isaac Roberts, 1899, from a 20-inch reflector. You know, you look at it today, you say, sure, that's a galaxy. But if you don't know what a galaxy is, you don't know what it is. Maybe it's some spiral thing where stars are being created inside of our galaxy. That's what most people thought. But it really was a shock, and it really was the opening up of a whole new window for our universe all the way back in 1912. Another important development in 1912, which many of you that have studied astronomy know very well about, is Henrietta Leavitt's publishing of this period luminosity relation for Cepheid variables. That's going to become very important, of course, when we find out what is the size and nature of our universe. Of course, the first Cepheid distance doesn't show up until 1918, but nonetheless, this is how we can actually get the distances to objects in the universe. Yes, we're measuring objects with tremendous red shifts, or blue shifts in the case of the Andromeda Nebula, but what do those mean? We don't know, because we don't know the distances to those objects yet. Okay, then of course Albert comes along with this general theory of relativity, 1915 to 1917. Lambda shows up in 1917, of course, to fit things along in with the steady state solution. And of course, as you know, this equation in itself is a couple lectures. I'm sure that the gravitation course is still taught here that I heard terrible stories about from the graduate students when I was an undergraduate. Okay, so, but very quickly after Albert publishes this theory, two solutions to that equation arise. One is model A, they termed it back then, Einstein's static matter-filled world, and just a couple of properties of that: homogeneously filled with matter, contained a definite mass, in equilibrium, no pressure stresses, you know, this kind of steady state model of our universe, that solution to Einstein's equations. And the second one is de Sitter's static empty model. Empty in a sense, although if you put particles in this model, they would give these kind of spurious positive radial velocities for distant objects in it, which was very peculiar. They were not regarded as coming from the expansion of space as we know it today in solutions to Einstein's equations. This was long before then. But they were just a property of that model. But people had some idea to keep this in mind when they were doing their observations. We'll see others did not keep these ideas in mind. They didn't know anything about cosmology. Okay, so Slipher by 1917, 5 years later, he's now collected 25 of these radial velocities for nebula, 21 redshifted, so they're not all redshifted or all blue shifted. 4 had velocities greater than 1,000 kilometers per second. So only 5 years ago, 300 kilometers per second approaching us seemed like a tremendous number. Now we're at velocities well over 1,000. No mention of these being interpreted in terms of this Einstein or this de Sitter universe. Remember I said de Sitter's solution is predicting these kind of spurious radial velocities. And you'll see in this talk again and again that there's this recurring theme. There's a disconnect between the observers and the theorists. The theorists are living in their world. They don't know anything about observational astronomy, although they're making predictions that observational astronomers could test. And the observational astronomers are doing their thing, and they have no idea what the theorists are actually working on. And that's why it will take so long for this subject to kind of move along in the right direction. By 25, there are 45 of these nebula, and again, 41 redshifts. So you can already see there's a trend that most of these spiral nebula that they're measuring redshifts for actually have redshifts instead of blue shifts.
Can I ask a quick question? So what about the 4 that are not redshifted? Are they blue shifted?
They're blue shifted, sorry, yeah. The 4 are blue shifted, the other ones are red shifted. Sorry?
What accounts for?
They're approaching us, they're coming towards us. There's some galaxies that are approaching us at high velocities. Yeah. Okay, so the next question is there a relation amongst these nebula of large velocities? Is there some kind of magnitude-velocity relationship going on, some kind of distance-velocity relationship? People are trying to figure out from the data, what is this data telling us about the universe? Okay, so I'm going to mention a few figures who you probably never heard of. They're lost souls of the astronomy world, you can think of it in a sense, but brilliant in their day and forgotten, unfortunately. So this guy, Wilhelm Wiertz, he was called the Hubble of his day, essentially. He's a German astronomer. He was one of the first to establish establish nebular motion as a whole using a kind of a decent sample size. So he used 16 nebular radial velocities by this published paper of Paddock in 1916 using Airy's equation, and he says, oh, it looks like these are traveling at an average rate of about 656 kilometers per second away from us. And he says here in 1918, if one gives this value a little interpretation, the system of spiral nebula disperses with this velocity relative to the momentary position of the solar system as its center. So he's saying, well, I see some kind of strange relationship here. He describes in a paper 3 years later a linear relationship between the nebular magnitudes, which he uses as a proxy for distance, and the velocities in an unpublished diagram, and he links it to the de Sitter effect. So he knows about de Sitter's theories. He's probably the only observational astronomer of his day who knows about general relativity. He's actually keeping up the literature and has said, oh, these look like it's related to de Sitter's effect. I bet they're the same thing. So again, an observer who actually knows his theory. This is a rarity in these early days. Okay, just to give you a little bit of context, because we're going to eventually start talking about the age of our universe as we go down. So we're in the 1920s by now, 1921. The Earth's crust has already been radioactively dated to about 4 billion years using thorium and uranium. By 29, Rutherford, he uses uranium-235 and 238. He gets about 3.5. But by the 30s, I want you to keep in mind that 2 to 3 billion years is the accepted age of the Earth using radioactive techniques. So as I go on to the talk, kind of keep those numbers in your mind. Okay, so more solutions to Einstein's general relativity equation will show up in the 1920s. Of course, the most famous one you know about today is Alexander Friedman's non-static matter-filled world model, his solutions to Einstein's equations. These are published in 2 papers. Here he shows that GR allows a closed universe with a time-dependent radius, so the universe has a time-dependent radius, it's changing with time. And he says, allow an open hyperbolic universe, a negative curvature universe. And again, these are in German journals, and these papers have been beautifully republished in this journal, General Relativity and Gravitation, back in 1999. So you can read a really nice translation in English of the solutions, because the solutions are very general solutions, and it turns out that Einstein's and de Sitter solutions are just sub-solutions of these things. So he comes up with a fantastic solution for Einstein's equations. And there's going to be a few quotes in this talk, which is not common practice, but I just have to read them to you. This 22 paper, he says, the purpose of this note, this paper, is to show that the Einstein and de Sitter worlds are special cases of more general assumptions, which he has solved, and to demonstrate the possibility of the world in which the curvature of space is constant with respect to the 3 spatial coordinates, but does depend on time. This new type is an analog of the Einstein world model, he says. For an illustration, he says, let's set lambda equal to 0. Let's give the universe a mass of 5 times 10 to the 21 solar masses. I'll just pull a number out of my hat that looks kind of reasonable for the day. And he gets a world model age of about 10 billion years. Remember that number. 1922, this guy pulls a rabbit out of his hat and says the universe is 10 billion years old. That's the best number we're going to see for a long time. Okay, but what about this guy? He's honest, right? But he says, I'm honest, our knowledge is completely insufficient for a numerical comparison to decide which world is ours. They are of a purely mathematical nature. This guy was a mathematician. No real attempt to incorporate up-to-date observational astronomy. I said he pulled that mass number out of the hat, essentially. He sent a copy to Einstein. A discussion ensued. He sent these solutions to Einstein. Einstein looks at them and he says, there's an error in your formula here. These solutions are wrong. Friedman gets them back, he looks at them, and he realizes Einstein is wrong. He hasn't read the papers carefully, and that his solution is perfectly fine. He sends them back to Einstein. Einstein admits that he was wrong and that his solutions are fine, and then Einstein forgets about these solutions, and they're not mentioned again. They disappear off the face of the planet Earth. This guy, unfortunately, he dies of typhoid just a few years later, so he's not around to promote this notion.
What did that statement on the previous slide mean about constant curvature but dependent on
if you want me to go into those specifics, it's a couple more slides, so I have to try to keep it. But you can ask me, we can talk after the talk if you're interested about the different kinds of curvatures you can have for different universe models. Okay, so many people are working on this problem. This guy, Ludwig Silberstein, 1924, he argues for a distance versus redshift relationship of a form that's related to the wavelength and the curvature of the universe, but with a red and a blue shift in his equations. It sounds very strange. He claims it with observations of globular clusters, but it turns out people later find out he only uses 7 of the 16 globular clusters to fit his data. That's one way to fit your data. You throw out half the data sample and it fits your hypothesis very nicely. People find out, of course, they ridicule this effect. This guy becomes a little humiliated about it, of course. This chap, Cornelius Lanzos, also has been thinking about these problems. So he's looking at Einstein's solutions. He uses a change of coordinate system.